Alright, today we're going to be reworking a work energy problem. The question is, you have 4 protons and they're all bound together, and it wants to know what is their speed when they're a very far distance apart. And the first time we worked it, we made a mistake because we assumed that you could compile all their charges together. You have to analyze the problem based on the way the charge between just 2 protons at a time. And the second time I worked it, I'll show you some of my work, what I did. Um, this is a little bit far along in the problem, but you have a point where you have, on this side, we would have had the original potential electric energy, and now this is the final, so this would have been EI minus EF, and it's equal to the, or EF minus EI, excuse me. This is, anyway, this is the final, and it's all kinetic energy now. We have 4 because of the 4 protons, but, and you'll see this solution works out. You get the right units, right, when we get down here, but you have a number, and it's 2.07 times 10 to the 8th meters per second, and the speed of light is about 3.0 times 10 to the 8th meters per second. And so we need to rework this problem using, instead of kinetic energy, we need to use relativistic energy. So from the beginning, let's see. Alright, let's get an idea of, see, here's our system. In the corners, the positives are the protons and their charge, and all the lines represent the distances between the protons, and you notice we'll have 6 different potential electric energy charges. Okay, so you start with work equals change in energy. Work equals the final energy minus the initial energy. We can expand work to force times the change in distance, and we can change the energy final to this equation mc squared times gamma minus 1, and that is our relativistic energy, and it's times 4 because we have 4 protons, and minus our potential electric energy, U, and the subscript is 1 through 6 for the 6 potential electric energies. And we can say, because we set the system as just the 4 protons, there's no outside force working on the system, and so our work will become 0, and at this point we move our initial potential electric energy over, and so the equation looks like our original potential energy is equal to the final relativistic energy. This is the problem. I've replaced the equations with expanded forms of the equations. I still have variables denoting charge and the distance between the protons, and the electric energy constant, and we have, mass and the speed of light squared, and we have a velocity vector on this side of the equation. And here is the algebra. I solved the equation. It's pretty complicated for a velocity vector, and I replaced these standards, or I replaced like this, the distance between like one proton apart, and you know, the mass of a proton for the mass part of this equation. And anyways, we get an answer that's now 2.32 times 10 to the 7th, which makes sense. It's about a factor of 10 slower than if we had just used the abbreviated equation for kinetic energy. Anyway, so we get 2.32 times 10 to the 7th, and that's how far 4 protons that are basically almost touching each other would be going once they're released, and they're not they don't have any potential electric energy between them anymore. Okay.